Now we are going to do the last proof technique, that is the principle of mathematical induction. Unlike the proof techniques that we have learned earlier, principle of mathematical induction can be used in a very specific kind of theorem. And the theorem is of the following form. You want to show that a statement Pn is true for all positive integers n. So the statement involves within itself a positive integer n. And when you have such a thing, you can use mathematical induction. You don't have to, but it gives you tools to prove such a theorem. So what is the principle of mathematical induction? It's best explained by an example. Let's say you want to prove that 1 plus 2 plus 3 up to n, that is sum of the first n positive integers, is n times n plus 1 over 2. We saw this statement in the previous videos without proof, and now we're going to prove it. And the way you prove this using mathematical induction is you actually prove two statements. The first statement you prove is called the base case. The base case says that prove that P1 is true. Okay, so take the statement that you have above and prove it for n equals to 1. And then the inductive step tells you that you prove the statement that if Pk is true, then Pk plus 1 is true. That is, if you can prove it up to some number, then the next number is also true. So you have to prove this if-then statement. Now, a very common mistake people make is that you only prove Pk plus 1 is true. That's not possible. What you need to prove is an if-then statement. So if Pk is true, then Pk plus 1 is true. And then once you prove these two steps, then I claim that you have proven the statement for all integers. And why is that? For all positive integers. So let me draw the positive integers. Now, the base case is showing that P1 is true. Then the inductive step says that if P1 is true, then P2 must also be true. So I'm using the inductive step for k equals to 1. That will give me P2 is true. Then I can use the inductive step on itself to prove that P3 is true. So now I'm plugging in k equals to 2 inductive step. Now I can use it again to say that P4 is true. I can use it again to say that P5 is true. And you can see that this will hit every positive integer, and so the statement will become true for all positive integers. And that's the idea behind induction. Now, the second common confusion students have is with proving the inductive step. So the induction is like a checklist. It's saying that you prove the base case and you prove the inductive step in any way you want. These are the two items on your checklist. It doesn't tell you how to prove the base case or how to do the inductive step. You have to use proof techniques that you learned somewhere else to do those two things. You can use direct proofs, proof by contradiction, proof by contrapositive, or proof by cases. Okay, and then when you do more advanced stuff, it might be the case that you have to use induction within induction, and that's totally fine. So let's do the example in more detail. So the theorem that I want to prove is the one I wrote about, that if n is a positive integer, then 1 plus 2 plus 3 all the way up to n is n times n plus 1 over 2. I have to do scratch work separately for base case and inductive step, because usually these two have nothing in common. So for the base case, I want to show that P1 is true. What is P1? The statement P1 is, I just plug in n equals to 1 there. Then P1 becomes 1 is equal to 1 times 1 plus 1 over 2. And I can see that it just simplifies to give the right answer. So I'll leave the scratch work here. Now comes the more interesting one. That is the inductive step. This is an if-then statement. So I want to show that if Pk is true, then Pk plus 1 is true. Now, how do you prove if-then statements? You assume the hypothesis and try to reach the conclusion. So I'll assume Pk is true, and then I'll try to prove pk plus 1. So let's expand these out. Pk is saying that 1 plus 2 plus 3 all the way up to k is k times k plus 1 over 2. And pk plus 1 is saying that 1 plus 2 plus 3 all the way up to k plus 1 is k plus 1 times k plus 1 plus 1, that is k plus 2 over 2. That's my goal, to go from the thing on the left to the thing on the right. Usually what you are trying to do is you're trying to connect the two expressions. So you have one expression on the right, which is that, and then you have one expression on the left, which is this. And you're trying to see how the left thing how the k expression fits inside the k plus 1 expression. In some way, you have to do like a pattern matching. There is no systematic way of doing this. And in this case, if you observe the right thing, you have 1 plus 2 plus all the way up to k plus 1. What you can see is that within here, what is the last thing before k plus 1? It's k. And this thing is the expression I have on the left-hand side. And so what I can do is I can replace, because I'm assuming the thing in the green to be true, I can replace this expression with k times k plus 1 over 2. And then I'll leave the other as is. This is all scratch work. That's why it's a little all over the place. But that's how you do scratch work. There's no linear way to come up with a proof. You have to look for patterns. It's like solving a jigsaw puzzle in some way. And now something is happening. Now something interesting, k plus 1 is common in here. And then I get k over 2 plus 1. Oh, and then now this thing is nothing but k plus 2 over 2, which is the thing I wanted. So I'm still not 100% clear about what's happening. But once I start, now I know the ideas. And once I start writing the proof, it will all become rigorous and streamlined. So let's start. We will prove this by induction. Oh, I did not introduce the variable, my mistake. You should always introduce all the variables. Okay, so we want to prove this by induction. So that tells me that, sorry. So that tells me that I need to do two cases. The base case is the smallest thing I want to prove it for. So n equals 1. For this, we need to show that 1 is equal to 1 times 1 plus. I'll just leave that this is true. That's just 1 is equal to 1. So the base case is done. Then I have the inductive step. For the inductive step, it's an if-then statement. So I'll say that we need to show. Again, I forgot to introduce the variable. Let k be a positive integer. We need to show that if pk is true, then pk plus 1 is true. So assume pk to be true. I assume 1 plus 2 k is k times k plus 1 over 2. Well, before I move on, I forgot to say in the introduction, this assumption has a very specific name. This is called the induction hypothesis. Again, we need to show that p k plus 1 is true, i.e. we need to show that 1 plus 2 plus up to k plus 1 is k plus 1 Or another very common source of confusion is there are so many equations floating around that it's hard to keep track of what is given and what is to be proven. And I don't have a good solution to this. So please be careful. Every time, it doesn't hurt to write to show or assume at the start of every statement, so that you are in your mind clear about what is given and what is to be proven. Okay, so I want to show this. So let's start with the left-hand side. The left-hand side is 1 plus 2 plus k plus 1. This is nothing but 1 plus 2 plus. And now I'll use the induction hypothesis and replace 1 plus 2 up to k by k times k plus 1. I am assuming pk is true. That's why I'm assuming that that statement is true, and I can do this. This is by the induction hypothesis. And then this simplifies. And this is the right-hand side. So I've shown that the left-hand side is the right-hand side. I'm not done. So this proves the inductive step. Finally, because we have shown the base case and the inductive step, we are done by the principle of mathematical induction. This is how all induction proofs go. There are small variants that we will see, but essentially they are kind of copies of each other. Of course, within the inductive step, you could do many complicated things. Let's do one more problem. And now I'm going to do a variant of mathematical induction. Okay, so what I'm trying to show is that for every positive real number x, and for every integer n which is greater than 1, 1 plus x to the n is greater than 1 plus n times x. Okay, now here you have two variables, so you have to be a little careful. You can only use mathematical induction for integer variables. So you are going to do induction for the variable n. X is a real number, and you can't do induction for a real number, so it will just come along for the ride. Now there is one more twist here. I am only trying to show this for n greater than 1. So I don't want to start at 1 because 1 does not satisfy the condition that 1 is greater than 1. What's the smallest integer that is greater than 1? 2. The base case is now n equals 2 because that is the smallest integer that satisfies the condition n is greater than 1. Okay, so this is the difference, that you don't always have to start at 1. You could even start at 0. You can start at 2. It depends on the question. Okay, so all induction needs is a smallest starting point, and then the inductive step does not change. From that starting point, you move one forward, then one forward, and so on and so on. So let's try to look at the base case. The base case is telling me that I want to show that 1 plus x squared is greater than 1 plus 2x. What can I do? I have the left-hand side. I can expand it as 1 plus 2x plus x squared. And now I see that my right-hand side is 1 plus 2x, and my left-hand side is 1 plus x squared. My left-hand side is 1 plus 2x plus x squared, and x squared I know is positive. And so the whole statement is going to be true because the left-hand side is the right-hand side plus something which is positive. And of course, I'll do this more systematically when I do the actual proof. So the scratch work seems to say the base case is fine. Now let's go to the inductive step. So remember that in the inductive step, I'm going to assume pk. I want to prove. So let's expand these out. pk is 1 plus x to the k is greater than 1 plus kx, and pk plus 1 is 1 plus x to the k plus 1 is greater than 1 plus. Remember, my induction variable is n, so it's the n that becomes the k and not the x. All right, so now I need to find a way of going from the left-hand side to the right-hand side. Again, induction is not going to tell me how to do it. It just tells me that I need to do this. So if I look at 1 plus x to the k plus 1, I can see that within it is 1 plus x to the k. So what I'm saying is I can go backward and I can see that this is 1 plus x to the k times 1 plus x. And now my inductive step, the induction hypothesis, is telling me that I can do something with this. That is, this is greater than 1 plus kx times 1 plus x. So I can go from here to here by multiplying both sides by 1 plus x. Okay. And now I can expand this out and I'll get 1 plus kx plus x plus kx squared. And that then is 1 plus k plus 1. I'm taking x common from the middle. And now let's see what we have. We have 1 plus k plus 1x here. We have 1 plus k plus 1x here. And then there is an extra term, which is a positive term. And so we will get that the left hand side is greater than the right hand side. Great. So this tells me that I have a strategy for proving. Of course, we don't prove things in all directions. We have to start from the beginning and go to the end. So let's do it systematically now. Let x be a real number and greater than 1 be an integer. We will show 1 plus nx, 1 plus x to the n is greater than 1 plus nx. So the first thing is base case. The base case here is n equals 2. And so we need to show that 1 plus x squared is greater than 1 plus 2x. Now the left hand side is 1 plus x squared, which is 1 plus 2x plus x squared, which is greater than 1 plus 2x, as x is positive. Actually, as x squared is positive, and this is the right hand side. So I've shown that the left hand side is greater than the right hand side, and this is exactly what we needed to prove. So this proves the base case. You really have to write all of these things because the goal is not to just be done with it. The goal is to communicate to someone else your ideas, and you can only do that by being very deliberate. Then you have to show the inductive step, where if k greater than 1 is a positive integer, then I need to show that if pk is true, I'll just expand it out. If actually, since I already done the scratch work, I'm going to be a little more concise with my steps here. So I'll say let k greater than 1 be a positive integer. Assume that pk is true. That is, assume that 1 plus x to the k is greater than 1 plus k times x. And just so that people know what I'm talking about, this is the inductive hypothesis. It's the name of this equation. So I'm assuming this to be true. This is a fact for me. Now we will show that 1 plus x to the k plus 1 is greater than 1 plus k plus 1 times x. So again, I'll start with the left hand side. The left hand side is 1 plus x to the k plus 1, which is 1 plus x to the k times 1 plus x. That's just by definition. Then now I'll use the induction hypothesis to get 1 plus kx times 1 plus x. So now I need to be careful with the reasoning here. In fact, I'm going to write this big. By the induction hypothesis, or we obtain this by multiplying the induction hypothesis multiplying both sides of the induction hypothesis by 1 plus x. We're not done yet. The induction hypothesis is an inequality, and you can only multiply an inequality by a number without changing the sign if that is positive. So I need to argue further that the sign does not change as 1 plus x is positive. Okay, if 1 plus x were negative, and if I multiply the induction hypothesis with 1 plus x, then I would flip the sign. So that's the argument for replacing 1 plus x to the k by 1 plus kx. Then I can simplify this, which gives me 1 plus x plus kx plus kx squared. And then I can take x common. And now I further get this is greater than 1 plus k plus 1 times x. And why? Because k plus 1 is positive, x squared is positive, and hence k plus 1 times x squared is positive. And this is the right hand side. So I have shown that the left hand side is greater than the right hand side, which is exactly what I wanted to prove. This proves the inductive step, and hence the original statement is true. By the principle of mathematical induction.